Good morning, everyone. So this week, I'm going to start talking about chapter 28, sources of magnetic field. So last week, we introduced magnetism, and we emphasized some similarities between magnetism and electricity, like, for example, field lines or dipoles. This week, we are going to be a little bit more technical and quantitative about that, and we are going to show that the similarity is actually very nice and very, very precise. Okay, so this is your reading assignment, and hopefully we can solve these problems tomorrow. So I told you, like, if there is like a current, like it could be like a straight wire or like a loop, there is supposed to be a magnetic field emanating or causing from this current. And I think, I'm not sure if we derived this, but something like this we derived. I think like the current of a straight wire was equal to mu0 divided by 2 pi times I over r. Okay. Here, mu0 is permeability of free space, and its value is 4 pi times 10 to minus 8 Tesla times meter over ampere. So this number is exact because this is actually the definition of magnetic field, which we'll come to that in a little bit. Maybe we can solve an example and see how this works. So this is example 1, calculation of B near a wire. An electric wire in the wall of a building carries a DC current of 25 ampere, vertically upward. What is the magnetic field due to this current at point P, 10 centimeter due north of the wire? Oh, I think I forgot to put the figure here, but it is something like that. Something like some current, electric wire in the wall, vertical upward. What is the magnetic field due to this current? Okay, something like that, P. This is 10 centimeter. Okay. So let's get this. B is equal to mu0 over 2 pi I over r. So this is 4 pi times 10 to minus 7 divided by 2 pi times I is 25 ampere divided by 10 centimeter, which is 0.1 meters. Okay, pi's and 2, this is like 50, 500, like 5 times O times 10 to the minus, okay, 1, maybe 10 to minus 5 Tesla. So you can see like a reasonable current, like a 25 ampere, gives rise to some like a detectable magnetic field. So here's another one, a magnetic field midway between two currents. Two parallel straight wires of 10 centimeter apart carry currents in the opposite direction, like here. This one is into the page, this one is out of page. Current I1 is 5 ampere is out of page, and I2 is equal to 7 ampere is into the page. Determine the magnitude and direction of magnetic field halfway between the two wires. Okay. So this is about like superposition. Let me just go ahead and do this. This is just like an application of the same equation. So B, okay. First, I can determine the directions. If I stick my thumb out and wrap my fingers, the B field of this wire is going to be in this direction. And if I stick my thumb into the page and wrap my fingers, the B field of the other one is like in the same direction. So total B is going to be addition of individual B's, they are in the same direction. So I'll write it like B1 plus 2 is equal to mu 0 over 2 pi. Okay. I is what? I1 is 5 ampere divided by, again, 10 centimeter, which is 0.1, plus the other one is 7.0 divided by, that's point, oh, okay, this is 0.5 actually. Their separation is 1, so this is 0.5. So then this thing is going to be, okay, 8, 4 point, I think it's something like that. 4.8 times 10 to the minus 5 Tesla. Is that correct? I guess I'm also warming up. Good, thank you. Okay, let me move on. So, okay, as you can see, like the point is, if you have a wire, there is a magnetic field due to current in a wire. And last week we said that if there is like a current in a wire, and if you put that wire in a magnetic field, that wire will experience a force. Then the logical next step is like, if you put two wires, there will be magnetic field from one wire. Of course, there will be magnetic field from the other wire, but the magnetic field from one wire will cause a force on the other wire due to the current in the other wire, right? So it's like, I think this is easier to say this way. Suppose you have two wires, I1 and I2, and I1 has like a magnetic field, right? Like this. You know how to use right-hand rule, and this magnetic field is non-zero at the location of I2, and there's like a current in I2, so we can use this force formula that relates magnetic field and current. Basically, B is, we just found, mu 0 over 2 pi times I1 over D, their separation is D, and the force is ILB, force on 2 by wire 1 is equal to current on I2, like second wire, length of the second wire times B1. So if you spell everything out, it's something like that. Mu 0 over 2 pi I1, I2 divided by D times L2. And like we know Newton's third law, so if this wire is acting a force on this wire, there has to be an equal and opposite force on the other wire. So basically these two wires, if the currents, okay, we can also determine the direction, right? For example, if you zoom in, so this is the direction of the current. Magnetic field is at the location of the wire is into the page. So if you do right-hand rule, like along the wire, curl your fingers, stick your thumb out, that's going to be like this. So this guy is going to be pulled in this direction. Similarly, this guy is going to be pulled in this direction. So if the currents of the wires are in the same direction, they are going to be attractive. Similarly, if you flip one of them, you just flip one thing in this equation. So you have to flip the forces. So wires with opposite current will repel each other. They're kind of like Coulomb charges, but now we are talking about currents on wires. By the way, I said this formula is exact. Actually, that's why it is exact, right? You can put two wires and define B with this equation and measure forces between two wires very accurately. And for this measurement, you have to, you can just define mu 0 to be like 4 pi times 10 to minus 7 Tesla times Ampere over meter. All right. So let's do a couple of more warm-up examples. So 2 wires of 2-meter long appliance cord are 3 millimeter apart and carry a current of 8 ampere, which is like a direct current. Calculate the force one wire exerts on the other. Okay. Okay, force is mu0 over 2 pi I1 I2 divided by the distance times 1. And now, okay, this is 4 pi times 10 to minus 7. Divide this by 2 pi. So I1 each is 8 ampere. So I1 is 8.0 times 8.0. And their separation is 3 millimeter apart. So this is 3 times 10 to minus 3 meters. And finally, the length is 2 meter long. It's like 2. So this is 85 times 10 to minus 7. Maybe this is like 10 to minus 3, 8.5 Newton. In like a reasonable setting, like in reasonable lengths, reasonable current, that's the orders of magnitude force we are talking about. And this force is, of course, measurable very precisely. So another example, a horizontal wire carries a current of 80 ampere DC. A second parallel wire 20 centimeters below, like this, must carry how much current, I2, so that it doesn't fall due to gravity. The lower wire has a mass of 0.12 gram per meter of length. Okay, we said if the wires are carrying currents in the same direction, it's going to be attractive. So magnetic force is going to be in that direction. And this is hanging down, so there's going to be like a gravity on the wire. So they have to balance each other. So for that, FB, the magnitude should be equal to mg. So FB is, okay, what is it? Mu0 divided by 2 pi. So I1 is 80 ampere times I2 divided by 0.02 meters, 0.2 meters. And what else do I have? Mu0, this 8I, and L1. And L1 is what? It's, okay, I guess it doesn't matter. I will write L1. And this should be equal to mg. M is some density times L1 times G. So that's why I don't need to know L1. Good. Then I2, I can just solve this for I2. I2 is equal to 2 pi over mu0, which is, I think I can actually write this. This is going to be 2 times 0.2 times rho is 0.12 times 10 to the minus 3 kilogram times 9.8 divided by, this whole thing is divided by 80. So let's do this. This one is, okay, did I take everything into account? Hopefully I did. So, mu0 is like, there's like a 10 to the 7 here, minus 7. I think I found the same thing, so it must be correct. So that's And 1, 2, 3. I think this is what it is. All right. Thanks. So this is what it is. Like essentially, what are we doing here? What's happening is like the wires are kind of like acting like charges in the case of Coulomb force, right? So in the case of electric forces, we said like electric forces are coming from charges, and these charges are applying forces to each other given by Coulomb's law. In the case of magnetic fields are coming from currents, and these source of magnetic fields, like which are currents, if you put two currents, they apply force to each other. Exactly the same way charges apply force to each other. Then the logical next step is like, you remember like the Gauss law, which relates charge in a finite region with the flux out of this region. So is there such a thing for magnetic fields too? So let's see that. So this is called Ampere's law. So Ampere's law is something like that. Suppose you have a current. Let's say this is just one current. For the simplicity, let's just imagine just single current in space. And Ampere suggested something like this. Suppose you have a loop around this current, and you break this loop into smaller chunks, like these smaller segments, which may or may not be straight. They don't have to be straight, right? But the important thing is like this is like a closed path, and inside this region there's like a current. And Ampere suggested something like this. If you add up each of these, like at every point there's like a magnetic field, and there is like a segment length here. So if you like take that product of this segment with magnetic field, that's like a scalar. And if you sum over all these little segments, Ampere suggested that it has to be equal to mu0 times I enclosed. And if you take the continuum limit, I think not surprisingly, this gives you an integral. And this integral is a closed line integral. So that's why we have this nice symbol. And what this says is like line integral of B around a current is equal to mu0 times the total enclosed current. Okay. And if you remember Gauss's law was something like that, but not quite. So Gauss's law was saying that flux out of a region, or like if you have like a charge Q, and if you have some surface area, this area integral, like or this volume integral, depending on how you look at it, this one is equal to enclosed charge divided by epsilon 0. So mu0 or like epsilon 0 is replaced with 1 over mu0, and charge enclosed is replaced with current enclosed. Okay. So this is called Ampere's law, and we can actually check if this thing is correct. Okay, maybe I can delete this one. This is for charges. We can check this against a known case, and the known case is magnetic field of a single straight wire. We just said it's like mu0 over 2 pi times I over r. And let's calculate this quantity. So this quantity, and okay, this is your current. There's like a closed path around this current, and we are supposed to calculate dl times b. Now dl is like, this is like r times d theta. This is r times d theta. And b, we just plug this in because that's the known case. And if you do this, you can see r is cancel, mu0 is constant, I is constant. What remains is like just an integral over d theta, and this integral will give you 2 pi, which will cancel this 2 pi. So you are going to get mu0 times I, as you should. So this means Ampere's law is actually working for a single straight wire. And now we can do the opposite thing. Suppose we know the Ampere's law, like suppose this is given. Can you find this, right? That's also a nice exercise. Yes, we can. I mean, and we just choose like a closed path around the current. And we choose this path so that this path is symmetrical. What this means is like magnetic field along the path should be constant so that I can take this integral. So if the magnetic field is constant, I can take B outside, and the L integral is going to be, just give me the circumference of this ring. So this is like B times 2 pi R is equal to mu 0 times I. That's the right-hand side of Ampere's law. Then B is equal to mu 0 over 2 pi times I over R as it should be. All right. So, and the important thing is like, okay, we postulated this law and then check this against what we know. But this is actually valid for the general case. Even if you have like bunch of currents in the space, and if you form a loop like this green dash loop, the Ampere's law is still valid. Line integral of B along this green dash line is exactly equal to mu 0 times I enclosed. So this line integral, if you integrate B along this line integral has nothing to do with this. Of course, the magnetic field has to do something with this, right? There's like a magnetic field coming from this here and here and here and here. But the point is, if you integrate over all, the positive and negative contributions of this outsider cancels and you only get something coming from the inside. So this is exactly like the Gauss's law. In the Gauss's law, it was like the flux, and we said what comes in has to come out. And only if you enclose something, then you have a net flux. You can think of like the same like here, but magnetic field is just remember it is the magnetic field, not electric field. Any questions? Okay, let's solve some examples. Okay, let's clear this one. So this is like a field inside and outside the wire. A long, straight, cylindrical wire conductor of radius r carries a current I of uniform current density in the conductor. And we would like to determine the magnetic field due to this current. A at points outside the conductor are bigger than R, and B points inside the conductor, like in this case. And we assume that R, the radial distance from the axis, is so much less than the length of the wire, and see if R is this, I is this, and B, what is B at that point? Is B always uniform? Not necessarily, right? Are you talking about this case? This picture? So B is not uniform, right? But to take the integral here, we chose a path in which B was uniform. The path is completely up to us. You can choose any path you want, as long as you can take this integral. For this case, I choose a path in which B was constant. And we'll play the same game here. So let's do this. So I said, let's start with A, inside. Or maybe it's A is outside. Okay, outside. A outside. So what we said is line integral B dot dl should be equal to mu 0 times I enclosed. I choose a path like this. It could be any path. The point is this wire is going from minus infinity to plus infinity. So I can ignore edge effects. And B is constant along this path. If you choose another one, B is different, but still it's constant along the path. Then we do B times 2 pi R is equal to mu 0 times I enclosed. Then B is equal to mu 0 over 2 pi. I enclosed is what? It's I divided by R. Okay, and B inside. Now I choose a pad inside, and I need to calculate the total enclosed current. And for that, I need to know the current that is passing through this area. And I know this is going to be, okay, total current is I divided by total area is current density times the area of this region, which is pi times R squared, is going to be my current enclosed, or I can write it like I times this guy is pi R squared. This is going to be, okay, cancel these, R squared over R squared. This is enclosed current. Then I can do the same thing. B dl is equal to mu 0 I enclosed. So this is going to be B times 2 pi R should be equal to mu 0 times I enclosed. We just calculated that is I R squared over R squared. Then B is equal to mu 0 over 2 pi. Cancel this with this. I times R over R squared. Right? So if you plot current versus magnetic field, let's do that. So this is radius. This is magnetic field. And there's like a radius of the cylinder. Let's call this R. So up to that radius, you have some linear increase, something like that. And once you hit the surface of the cylinder, it's like decreasing with 1 over R. So you have something like that. And finally, if R is equal to 2 millimeter, I is 6 ampere, what is B at R, R, and R? Okay, maybe I can calculate one of them. So let's calculate the first one. So B, okay, C, B is equal to, so this one is, I guess it's inside. R is 2 millimeter and we are talking about 1 millimeter. So I'm going to use this formula. So this is 4 pi times 10 to minus 7 divided by 2 pi times current is 60 ampere times R is, okay, it's a ratio 1.0 times 10 to minus 3 divided by R is 2.0 squared times 10 to the minus 6. 30 times 10 to minus 7 minus 3 is minus 10 plus 6 minus 4 Tesla. Your homework, get R is equal to 2.0 millimeters and R is equal to 3.0 millimeters. So one is right at the boundary, this one. So you can use either of these. The other one is outside, so you have to use this one. There is actually a real life application of this, and they are called coaxial cables. A coaxial cable is something like this. Maybe I can read it. A coaxial cable is a single wire surrounded by a cylindrical metallic braid. Okay, this is like cylindrical metallic braid, as shown here, and the two conductors are separated by an insulator. I think this yellow thing is like an insulator, insulating sleeve. The central wire carries a current to the other end of the cable in that direction. And the outer braid carries return current. So this goes somewhere, and it returns through this braid and is usually considered the ground. So describe the magnetic field in the space between the conductors and outside the cable, right? So a magnetic field inside is like, if you look at this, it only knows about what, right? It's going to be only about this current. If you apply Ampere's law, it is not going to know anything about outside, right? So the magnetic field inside is like just this current. What about the magnetic field outside? So if you use the Ampere's law for a circle like this, what is the total magnetic field outside? Zero, right? Exactly. Thank you. Because there's like a current this way, current that way. So total enclosed current is zero. So magnetic field will be zero. I mean, quite zero, depending on how good your cable is. And that's why, when you have like sensitive signals to carry, like sound signals, like if you are like playing music and you want to use your amplifier, you generally use this kind of wire because you don't want noise from your speakers. This can like shield outside noise pretty well. Or your like TV cables, that's also like a sensitive signal. You better have something that doesn't get affected by the outside noise. So here's like a exercise. In figure 13, A and B are wires, each carrying a 3 ampere current, but in opposite directions. And the question is, on the circle C, okay, there are like currents in the opposite direction. This one's out of the page, this is into the page, and there's like a curve like this. Which statement is true? A, B is equal to 0. B dot dl is equal to 0. C, okay, B is 3 times mu 0. I wonder how they got this. And D, B is equal to minus 3 mu 0. And E, B dot dl is equal to 6 mu 0. So which of these statements is true? A, B, C, D, or E? B, right? So the total enclosed current is plus I minus I 0. So the total enclosed line integral of B should be 0. That's the Ampere's law. All right, so here's another use of Ampere's law. So this is example 8. Use Ampere's law to show that in any region of space where there are no currents, the magnetic field cannot be both unidirectional and non-uniform as shown in this figure. Let's just examine this picture and try to see what's going on. So now you remember that number of lines indicate the strength of field, right? So the density of lines. So the density of lines here is like bigger, so the field must be stronger here. And the density of lines here is smaller, so the magnetic field must be smaller here. So maybe I can think about this. So B dot dl is what? It's equal to, from A to B, B dot dl plus B to C, B dot dl plus C to D, B dot dl, and D to A, B dot dl. So maybe I can ask you, like, what is the relationship between A to B and A to D? or what is B dot dl from A to B and B to A to B, like from here to here and from here to here. What do you get if you do these two line integrals? 0, right? Why? Yes, exactly, right? B and L are perpendicular, so you don't have any contribution from this guy or this guy. Then this thing is going to be equal to A to B, B dot dl plus D to A, B dot dl. But along these paths, this and this path, B is constant. So I can take it out of the integral and then multiply this with L to get the integral. So this is going to be equal to B, let's say, so let's call these guys, this is like, okay, B to C. Okay, let me be careful with my labels. So this is B to C, the other one, B to C, D to A, good. So this is going to be B, let's call this one smaller because it's the smaller magnetic field. B small times some length. The other one is in the opposite direction, right? So minus B large times L. So you can see this is equal to some minus B large minus B small times L. So what's wrong with this result? What is peculiar here? No current, but there is magnetic. Yes, exactly. Thank you. So we found something non-zero. As you can see, this is like a large number minus a small number. So this thing is non-zero. L is non-zero. The entire result is non-zero. But if you look at this region here, there is no current. So I enclosed is equal to 0. This doesn't satisfy Ampere's law. So then there is no way you can get something like this. Okay? This is physically impossible. And now you can think why it has to be like this, right? Think about that. Think how this changes the picture. Okay, this is also homework. Consider how curved lines change our conclusion. All right, let's move on. So I want to now introduce some specific tools, so-called solenoid and toroids. So the solenoid is a device that you obtain by wrapping a current around a cylinder, something like that. Like you have some current and you wrap it around like this, right? So there's like a current here. So what happens is like, okay, you can think of these like if you want to simplify, like loops, right? And we know each loop is going to give some magnetic field. You can use your right hand to find that it's going to be in this direction. And there's going to be a magnetic field. So the current, the circulating current is going to give rise to a magnetic field. That's the solenoid. And we are talking about like an ideal solenoid here. Of course, if you have like a solenoid with finite width and like some wire separation, it's a little bit complicated problem with all these like bending and curving magnetic field lines. But we are thinking about like an ideal solenoid, something like this, right? There's no gap between the wires. It's like uniform. And let's, for simplicity, let's consider some solenoid that goes from minus infinity to plus infinity. So we don't have to worry about these guys either. Everything is going to be like this. Okay. So I'd like to find the magnetic field inside an ideal solenoid. For that, I have to choose like an Ampere region. Like it's like Gauss surface, but like now this is like Ampere's line, let's say. Maybe I can call it Ampere's curve. So we choose something like this, right? Or I could choose something like that too as well. That's perfectly fine. You just keep track of your choice. And I want to calculate the total line integral of magnetic field along this closed box. It has like, again, like how many contributions? 1, 2, 3, 4 contributions. I can write them down. From C to D, from D to A, D dot BL, from A to B, B dot DL, and from B to C, A dot BL. Now here there's like a different cancellation. If you look at this, the only difference between this guy and this guy is one is coming in, the other one is coming out, or like this one is coming in, this one is coming out. Everything else, including B, is the same. So if you put L goes to DL, so in this integral, you are going to flip the sign and cancel this guy, right? So these line integrals are in the opposite direction, so they are minus of each other. So you can cancel these two guys. And now I have only two paths, from C to T and from A to B. And for an ideal solenoid that goes from minus infinity to plus infinity, there cannot be any magnetic field here. That's also 0. So this guy is 0 because magnetic field is 0. There's a different reason here. So I only ended up with this guy. So this is B dot L. And B is constant inside because there's no reason for it to change from here to here. So I can just take it outside. And I have something like that. B times length of this segment, B times L. And this should be equal to total enclosed current here. But what is the total enclosed current? Number of lines per unit length times length is my total current. So mu0 times this is I enclosed, but I enclosed is like line densities times length. And if you multiply it current, you find the total current. So at the end, inside this solenoid, you have something like this. B is equal to mu0 n times I. All right? And if you want to find the direction, you just use the right-hand rule to find it. It's in this direction. Maybe we can do a calculation to see orders of magnitudes with some reasonable numbers. So a field inside a solenoid, a thin 10 centimeter long solenoid used for fast electromechanical switching has a total of 400 turns of wire and carries a current of 2 ampere. Calculate the field inside near the center. Okay, that's what we care. The field inside near the center of the solenoid. So we already have a formula for that. B is equal to mu0 times n times I. So mu0 is 4 pi times 10 to minus 7. And this should be equal to what? Tesla times meter per ampere. N is what? It's like 400 divided by 10 centimeter, which is 10 times 10 to minus 3 meters. Oh my God, I'm like having like a centimeter crisis today. It's like 10 to minus 2 meters. Okay, I guess that's a little better, right? And finally, current is, okay, this is times ampere, which is 2.0 ampere. Okay. Cancel these guys. It's like Tesla as it should be. And what is the result of this calculation? Let's calculate. 1.0, okay. 1.0 times 10 to the minus 7. This is minus 5. And 3 more minus 2 Tesla. Now you know this is like a reasonable magnetic field, right? This is actually strong with our case. If you want to like, if you have like a device like this, you can easily stick it on your fridge and it's going to be stronger than your refrigerator magnet. All right, now let's talk about toroid. Toroid comes from torus, and torus is basically donut. If you have like a cylinder, and if you stick 2 ends of a cylinder, that's a donut. And if you wrap some current around this donut, you have a toroid. And now we would like to use Ampere's law to determine the magnetic field inside and outside the toroid. Maybe I can first start with outside. And for that, I want to use this pad 2. Let's choose like a pad like this. And I want to ask you, what is the net enclosed current in this pad? Zero, right? So, okay, thank you. Maybe I can write it like this. So B dot dl is equal to mu0 times I enclosed. So you can see for every current out of page, there is a current into the page. So it's out of page, into the page, out of page, into the page. So each one comes in pairs, so the net current is 0. So this guy is 0. This side is, okay, this is like a symmetrically chosen Amperian loop. So it's going to be equal to some B dot, I don't know, 2 pi R. Then if right-hand side is 0, B should be also 0. B is equal to 0. Now let's do the same thing inside. Here I choose the pad indicated with pad 1. And I do the same thing. B dot dl is equal to mu0 times I enclosed. Okay, B is, I'm assuming it's constant inside, so this B times 2 pi R, right? This is like some R. This total length is 2 pi R. And I need to calculate the total current inside. It's going to be mu times however many loops I have, I don't know, 1, 2, 3, 4, 5, 6, n, times the current flowing through the wire, which is I. Then B inside the toroid is mu0 over 2 pi n times I over R. And for direction, we should use the right-hand rule. So this guy is going like this, right? Like this. If I wrap my fingers, it's going to be like this. So the magnetic field is, okay, according to our point of view, it is going to be clockwise direction. By the way, in the case of toroid, actually, you can imagine like if you have like a cylinder, it's like the distance between these two guys are going to be the same. But if you bend the cylinder, the distance from here to here is going to be more than distance from here to here, right? As a result, actually, magnetic field will be a little bit non-uniform inside the toroid. But we neglect that, right? Magnetic field around here is a little stronger than magnetic field here. So now, okay, let's just look what we got so far. We started with magnets and magnetic fields. And we said, if you pass a current through a wire and put your wire in a magnetic field, the wire is going to experience a force. And then we said, okay, the logical next step was like the wire should itself have a magnetic field. And what we said is like if you have two wires with current, they have interaction through magnetic fields that they generate. And next we said actually there is like a nice mathematics structure very similar to Gauss's law, and we showed that it's called Ampere's law and it's useful. And the next thing is like, what about the Coulomb's law, right? In the case of charges, if we have two charges, Q1, Q2, they exert forces on each other given by Coulomb's law. Is there a Coulomb's law for currents and magnetic fields? Yes, and it is called Biot-Savart law. Okay. And is there like an electric field? Okay, a single charge has an electric field, like Coulomb field, if you like. Is there a magnetic field due to a single segment of current? Yes, there is, and it's given by Biot-Savart law again. Okay, and I'm going to write you the magnetic field from Biot-Savart law. So it's something like this. If you have like, you can have some long currents, and we are like considering a segment of this current. Okay, let me try to make this just a little bigger. Maybe here. Okay. So we are considering some loop, and there's like a tiny little segment here. And I want to ask, what is the magnetic field at point P due to this little segment here? So we write it like this. I think we consider this for straight wire, but if it's not like a full length straight wire, we can still write this. We have to define some geometrical objects here. First, this segment has like a direction shown with dl, like this vector. And from your location, you point to the point of interest, P, and your distance is like a vector r. And there's like a unit vector towards that point, which is r hat. And for the direction, okay, we can calculate the direction from right-hand rule, right? If you stick your thumb here and wrap your fingers, you're going to have something out of page towards you here. So that's the direction. But to write all these things nicely is like, okay, mu0/4 pi is just the overall factor, I is the current, and you can just judge yourself, like if you do like dl cross r here, dl cross r is going to give you the direction nicely, and you have to divide it by the distance squared, r squared. Okay. So if you want to find the magnitude, this dl and the r, they have like some angle theta. So you can take this cross product and forget about vectors. So it's going to be mu 0 over 4 pi I dl over r squared, and there's like a sine theta. Now I have to remember the direction, and for the direction I have to use my right hand rule. So it's going to be out of page. Right? And now I can like sum over all segments. If I have like some curves, like weird geometrical shape, I can integrate it. I can integrate this and then find total magnetic field at point P. And that's the integral. All right. So let's do some examples and see. Okay, let me clean this up. Okay, the simplest thing we can do is like a straight wire. Let's use straight wire to see how this formula works. B due to current I in a straight wire. For the field near a long straight wire carrying current I, show that the Biot-Savart law gives the same result, that is like B is equal to mu 0 I over 2 pi R. So let's start. dB is equal to mu 0 over 4 pi, and the current times the, okay, this looks like cross product, so let me just not, so this is dl cross with r divided by r squared. So that's a vector. Now my dl is dy, and it is plus y hat direction. And there is like a r hat here, which is like given by theta. So I can write this as mu 0 over 4 pi times I times, okay, dl cross r is dy times sine theta, and divide this whole thing with r squared. And my r squared is equal to, I can use Pythagorean theorem to write r squared as y squared plus r squared. Okay, let's write a tangent. Okay, maybe I can write y in terms of tangent. So r divided by y, actually it is like, seems like minus y here, is equal to tangent theta, or minus y is equal to r times cosine theta divided by sine theta. If I take the derivative, minus dy is equal to r, okay, cosine minus sine theta minus cosine theta, divide this whole thing with sine squared theta d theta. So this whole thing is minus 1. So my dy is equal to r over sine squared theta d theta. Okay. Okay, now let's just try to take this integral or this integral. So b is equal to mu 0 I over 4 pi. Okay, maybe I can first write in terms of y, it's like minus infinity to plus infinity dy sine theta divided by r squared. Now I do this change of variables. It's going to be mu 0 I over 4 pi. Okay, dy, whenever I see dy, I just put r d theta divided by sine squared theta. There's like sine theta, and there's like r, and for r, okay, what is r? R over r is sine theta, then r is r over sine theta, and I need to take the square of this guy. This is r squared, 1 over r squared of this theta. So this is sine squared theta divided by r squared. Some cancellations, some more cancellations, and I need to put the integral limits. As y goes from minus infinity to plus infinity, my theta goes from, okay, if you take this point all the way to here, you can see this angle getting smaller and smaller, so it should be from 0. And if you are all the way there, it's going to be what? 0, 0, 2 pi, right? It's like this is theta. Okay, here is my theta. Here's my theta. Here's my theta. Here's my theta. As I go, yes, it's going to go to pi. And now let's take this integral. This is equal to mu 0 I over 4 pi. So sine minus cosine phi, cosine theta from 0 to pi. This thing is equal to minus 1 plus 1 minus 1, which is equal to 2. So this whole thing is equal to b is equal to mu 0. Okay, I forgot an overall r. So this r should be here, here, mu 0 I over 4 pi r. Okay. And for the direction you can use right-hand rule if you like, but cross product already told us it's into the page. So determine B for points on the axis of a circular loop of wire of radius r carrying a current I, as in figure. Okay. So let's again write the B as a vector is equal to mu 0 over 4 pi I dl cross r divided by r squared. Now dl is here at any point is like a circle. Okay, if you have like a circle, something like that, your dl, if you look from here, dl is like counterclockwise, right? So this one is out of page, this one is into the page, so that's dl. And your r is this vector. So at any point on the circle, r and dl are perpendicular. So dl is perpendicular to r on circle. So we can take this cross product, which is just linear product, normal product. So this is going to be equal to mu 0 I over 4 pi. Now I need to write dl. Let's parameterize the circle from the radius and the angle. So this is r times d theta. There's like a circle. So this is theta. This is d theta. So this is dl. dl is equal to r d theta. And divide this whole thing with r squared. There are two R's now. One is capital R, the other is small r. But this thing is going to be like this little segment. From right-hand rule, I can just write this R, and this is going to be perpendicular to this R. So there are two projections. One is along the axis, one is perpendicular to the axis. And for another segment here, there's going to be a like equal and opposite magnetic field like this. There'll be like perpendicular and parallel. These perpendicular components cancel. So we have the sum over all components along the axis. So for that, we need to project to here. And the way we project is like calculate this angle. This angle you can just geometrically judge. This is angle to theta. So you just multiply it with cosine theta, cosine phi. Okay. And cosine phi is equal to what? It's equal to R over R squared plus X squared. Okay. Maybe I can actually write it here. And I just delete this and indicate this thing is cosine phi projection along the axis. And R squared is what? R squared is also R squared over X squared. So let's write this. R squared plus X squared. So you can see nicely nothing is dependent on theta. So we can take this integral. So B is equal to mu 0 I over 4 pi. This is going to be 2 pi coming from integral. And this is R squared plus X squared to power 3/2. And the direction is to the right. And maybe I can even simplify. This is going to be 2 pi. It's going to be 2. So now I want to remind you the dipole magnetic moment of a circle was given with some, again, mu. This mu and this mu are different. Does anybody remember the dipole magnetic moment? Yes, I times A, thank you. And this is going to be I times pi R squared. So if I use it, this thing is going to be mu 0 times, okay, what should I do? I should do pi R squared I divided by 2 pi R squared divided by R squared plus X squared to the 3/2. Is that even right? Oh, I think I forgot factors of R squared here. Okay, if nobody's fixing my mistakes, I have to do it myself. So here, there's like R and R. I forgot to write this. Okay, this is R squared. Good. Now I don't have this R, pi R. So this thing is equal to mu 0 over 2 pi mu divided by R squared plus X squared to the power 3/2. Okay. And now let's look at the limit. Let's look at the limit in which X is much, much bigger than radius. Then I can neglect that R, then B is going to be equal to mu 0 over 2 pi magnetic dipole moment of the loop divided by X cube. right? Magnetic dipole field. So maybe I can try to remind you what is the electric field of an electric dipole, just to compare. So E, I guess I can just write it. It's like 4 pi epsilon naught is equal to P electric dipole divided by x cube. So this is electric dipole field. So this is B field, this is E field. All right? So when we say like a loop is kind of like a dipole, it's actually a good statement. You can see the similarity, right? I think I have one more example and then we can finish. Do we have time for this or should I do this tomorrow? Okay, let's do this tomorrow. I think that's a good point to stop. If you have questions, we can talk. Otherwise, I will continue tomorrow.